Hey everybody, welcome to the 5th CBP Nonprofit Research Publication Overview. If you've been following these, you know that I've been giving a history and overview of chiropractic biophysics nonprofit research publications. Again, I'm Dr. Deed Harrison. I'm the president of Chiropractic Biophysics Nonprofit and president of Chiropractic Biophysics Seminars and Technique. The two are separate entities, even though I am president of both of them. This particular one is one of our most famous research projects. It's perhaps been one of the most cited research projects that we've done. This was the CBP Cervical Spinal Model validation paper, or a paper to see can we validate the concept of the cervical curve being approximated by a piece of a circle. This comes from Spine, 1996, in the March issue. This was done by my late father, Dr. Don Harrison, and Dr. Tad Yannick, his PhD advisor, Dr. Steve Tronovich, a former CBP instructor, and Dr. Bert Holland, our PhD in statistics from Temple University. Unfortunately, my father and Bert Holland are now passed away. However, this is a great particular project for us to be going through here. Our model runs from C2 down to T1, and we say C2 because there's no PLL at C1 because there's no posterior body. However, we do have the tectorial membrane up in that region that is an extension of the PLL. So you can say that that is the path of our model along the back of the dens, if you will. Okay, so the posterior aspect of the vertebral bodies from C2 all the way down to T1. And then we can get the length of the curve using a drafting tool that is very, very accurate to 1/10 of a millimeter that goes along the posterior aspect of the vertebral body margins. So we're going to look at what is the average height over length ratio of these 400 subjects. We're going to look at what is their segmental and total angle of curve, and then we're going to take this information and we're going to plug that into our cervical spine model, which is simply a computer code that's a Fortran equation, and we're going to put a subject's height over length index into our model, and we're going to see what those segmental angles should be. So we're going to have a model prediction, and then we're going to have a hand-drawn measurement, and we're going to compare the two to see can the model accurately predict what we've identified in the subjects. And that is a form of validation. If the model, if you give it a height to length index and it spits out numbers that are based on certain criteria that we'll talk about, if that model is accurate to what we actually measure in those subjects, then we can say this is a valid model within certain limits. Now, the exclusion criteria are important in this project. Many people have misunderstood the study design. This is a retrospective sample of 400 subjects. We excluded any subject that had segmental or total cervical kyphosis. Why? Because we're only looking at a model of what a lordotic neck looks like. By nature, cervical kyphosis is abnormal, so we excluded that from our population. Any segmental or any total kyphosis, you are not in this paper. Only people with lordotic cervical curves are in this project, 400 of them. We also excluded moderate to severe degenerative. So our cervical model, we have major and minor assumptions, and I've broken them down into 6 assumptions. Number 1, the cervical lordosis is a circular arc. We need to test that. This is part of the assumption of the model. It is a piece of a circle along C2 to C7. The cervical lordosis extends actually from C1 to the inferior body corner of T1, okay? C1 to T1. The thoracic vertebra number 1 is actually a transition or inflection point between the two curves. The superior half of T1 looks like the cervical segments. The inferior half of T1 kind of looks like, or does look like, the thoracic segments when you look at the anatomy of it. So one of our assumptions is the whole curve C1 to T1, but we'll likely find out that C2 to C7 in later projects is a little bit better model. This height, okay? We know C2 is a bigger bone. How much larger it is, this is what we had to approximate or estimate in our model. So we looked at it logically and anatomically in papers, and we said, well, there's no disc from C1 to C2, so the C2 vertebral body theoretically is about the height increase of an extra disc. In other words, it's 40% larger than the other vertebra. We'll see how that assumption came out. The line through the atlas vertebra used to measure. What I do want to do is show you the model prediction. So our model predicts that for these people, ideally in our model, you would have a 96.73% height over length ratio. That would give me a 23-degree atlas plane line. That would give me a 34-degree ARA. That would give me C2, C3, 7.5 degrees, and then every segment below that is 6.6, okay? Now this is our model predictions. Now what we do is we compare the data in this model prediction column to the data over here in this mean column. And then what we do is we look how close these two are aligned. 33.99, the model predicts 34. I'll tell you what, that's spot on, right? There's really 0% error there. I mean, there's a tiny error, but we rounded it to 0. The C2, C3, how close does our model, using 40% larger for C2, approximate the actual data? A 3.7% error. How close does it approximate the rest of the segmental values? Look at this, 0.5%, 8.5, 10.7, and 0.5. Now the only outlier appears to be this C5, C6 level, 10.7%. Okay, so I look at that and I go, whoa, 5.9, model predicts 6.6. You could say 10.7%, that's a little bit high, but still you gotta realize this. That's really damn close from a math modeling perspective. A 10% error is a benchmark in mathematics. That means you got an A-, folks, right? And the reality of it is this. We didn't make the damn spine, we're just modeling it, right? People look at that and you go, oh, way off. Really, 10.7%? Would you really get upset if you got a 90% on your calculus test? Would you go home and cry about it, or would you go out and have a beer? That's the reality of it. Does gender dictate the amount of cervical curve you should have? Now, at first, people would say, oh, well, yeah, it totally does, right? But when you really look at it logically, should a woman compared to a man have different sagittal plane curvatures? Do they really have different loads acting on their spine? Do they walk different under gravity? Do they have different gravitational loads acting on them? Do they have truly different anatomy in the neck? You know, when you break it down, it doesn't make sense. We have the same ligaments, the muscles, the discs, the bones. We have similar attachments. The difference is the body mass index and the physical size and the density. It doesn't mean that their curves should be different. However, we have to investigate that. So what we look at is we go right to the 90 or height over length index. In the end, what does it mean? Well, here's what I would suggest to you this paper means. There truly can only be one ideal for the cervical curve. However, there's going to be a within normal limits. Within normal limits is likely somewhere between the top three here. So my top three starting from the left is likely going to be considered within normal limits. However, straight necks and different types of kyphotic necks, based on what we've identified in this paper, are truly abnormal. And it's because in normal subjects, they should have a cervical lordosis, and we can model it with a piece of a circle. It should be a uniform rate of curvature. C2 is approximately a degree bigger than the rest of the cervical vertebra, and that's due to the size of the vertebral body. This is important data. Now, we still don't know today, is ideal really ideal? What we know is that below a certain range, there are consequences and there are problems, and we'll talk to you about that later on. However, we're confident that this can be used as normative data. It's one of the largest sample populations ever done on the cervical spine in true lordotic neck specimens. It's a very well done project for its time and for what the data could provide and give us. The other thing that this particular project really screams out, and people often forget about this, is the fact that certain curves are extremely abnormal, and you have to be able to spot those right away. Oftentimes, when you look at radiology reports or other doctor reports, you'll see an overtly abnormal cervical curve, and it's classified and qualified as normal. Really? Let me show you a little girl that fell off of the monkey bars and landed on her head, and she was cleared as normal at the hospital. Lo and behold, you take an x-ray, what do you see? You see C3, C4 is contributing the entire amount to the total curve. If you just, do a total angle of the curve, you go, oh, it's within normal limits. But when you actually look at it, it doesn't take a genius to figure out that C3, C4 is well beyond 11 degrees. It's an unstable segment. It's got a retrolisthesis. This is a serious injury, and this is a serious application for our particular paper. You can spot these things right away, and you can say, hey, this is truly abnormal. We need to get a much smoother, amount or alignment in that curve, and we need to reduce that C3 to C4 angle. Hopefully you like that project, 1996 spine. I would strongly encourage everybody out there to read that paper in detail for yourself. That way you can truly identify, hey, is this really a legitimate paper? Is this a normative data set that I really want to hang my hat on and compare my patient populations to? If you like this project and you like these videos, I'm going to ask you again to please consider supporting Chiropractic Biophysics nonprofit. We need membership. We need the members to pay their dues. This is how we do research projects like this. Research is time, effort, energy, but also monetary consuming. And the way you can help out there is by contributing financially to CBP nonprofit and help us spearhead new cutting-edge research projects and test older projects like this as well. We're still improving our methods as well as advancing our methods, right? So please continue to support us or consider supporting us, either directly through donations at the web link or indirectly through Amazon Smile. Thank you very much for your attention. I'll talk to you next week.